Hi everyone. So you've seen this slide before, and we talked about the fact that resolving power of a telescope is associated with diameter, and we're going to really work on that now. When we talked about angular resolution and having the very, very low angle, very small angle, but very fine detail, that is low angles usually associated with large mirror diameters. So they are inversely proportional. Okay, when you have a high number in the denominator, it's going to give you a low number in the quotient. So in talking about that, let's talk about how we can make that diameter even larger. And there is a method called interferometry that goes along with the wave property of light that can interfere with each other, and we addressed that a few videos back. We said that when waves come from two different areas, those waves can meet and both cancel each other out, which is the dark sections in here where they cancel each other out, or they can reinforce each other, and those are the bright sections in here. And this interfering wave-like property can be exploited by telescopes, especially optical telescopes and radio telescopes, so that we'd love to have one big diameter, but interferometry is actually allowing us to use many smaller telescopes in arrays, and those arrays allow us to produce one huge diameter. Let's explain how. You've got two small telescopes, optical or radio, and you've got a good software connection between them and some very, very accurate mirrors and timing between them. They are both looking at the same object. Picture the Keck telescopes up on top of Mauna Kea. They're used for this all the time. They're both looking at the same object. They're looking for a black hole in the Andromeda galaxy. Often, that's what a lot of their research is. So they're looking at the same object, but because they are separated, they are getting the wavelengths in at just a hair off on time. We're talking like nanoseconds here. And as a result of that, this software can take that timing difference and it can refine the light pattern that's associated with that and fix the phases so that they match. And when the phases match, they can peak together and reinforce the wave. And in reinforcing the wave, you can actually increase your power of that wave and increase the effective diameter of the telescope. The result of this is that you effectively create a larger diameter for your telescope with less diffusion, because the diffusion again is going to be around the fringe outer areas, and you get a lower angular resolution out of this. Really brilliant images. So by doing this, by taking these two, this represents the Keck telescopes here, the two of them up there. They are both looking at the same object. When the light waves come in, they will come in just a bit out of step because these two are at different locations, just nanoseconds away from being in step. The software can consider the timing differences, adjust the phases. Now they are in step, peak to peak, peak to peak. They can reinforce each other and make that light wave more powerful, in effect producing a larger diameter scope. And in fact, underneath Keck 1 and Keck 2, there are a series of mirrors that are coming out of that Nasmyth focus that we talked about, underneath in very, very accurate mirrors, to very accurate timing, to very precise software that can adjust the phases to make them interfere and strengthen them, so that instead of having one 10-meter telescope and another 10-meter telescope, maybe getting 20 meters of resolution, you actually can get out of Keck 1 and Keck 2 85 meters of resolution, which is the distance between the outer rim, the diameter of the Keck 1, and the diameter outer rim of Keck 2, 85 meters. So that when you're looking at this, here's the diameter that you effectively get is the largest distance between the dishes. Another interferometer that I really would love to go see, I tried to go see it in January, is the VLA, the Very Large Array out in New Mexico. And I talked to some friends about it, and they said, Mary Beth, there's nothing out there to see. And they're not going to let you onto this base because the security is so high. So we think that maybe this isn't a tourist attraction. So anyway, this is a very large array, and this can be done in a number of angles. So you could go from this dish all the way to this dish and have a massive diameter across it when the software can align the phases and can make them interfere with each other to peak an effective diameter much larger. When we improve this angular resolution, we can measure the improvement. And this is an example here of improving that angular resolution so you get the lower angles with fine diameter. When we look at this image, we are improving the angular resolution as we get to this area. When you look at this, we are looking at the angular resolution between this bright star and this galaxy. And it's not so fine for this detail here. This is within what's called 10 arc minutes. Let's go over what an arc minute is. If there are 360 degrees to a circle, then each of those degrees, and this is not to scale, this 1 degree can be moved from a degree into a minute, much like a clock. Okay, so this can be moved into 60 minutes. And this is saying here that across a circle on a diameter, this is within 10 arc minutes. All right, so you have about 10% of that 1 degree there, and you've got a really blurry image. So 10 arc minutes is considered a rather large angular resolution. And from those 60 minutes within the degree, you can divide out each minute into arc seconds. And so one of them is a single quote. The arc minutes is a single quote. The arc seconds are a double quote. You can get it all the way down here to a resolution of about 1 arc second, which, if you think about it, is a 60th of an arc minute, and that is a 360th of an entire circle. So we can really narrow this down, and we can measure the amount of angular resolution we have, and we say that this angular resolution is within 1 arc second. It's really a goal that you're looking for in fine optics. Radio images can be easier to manipulate with those larger wavelengths, but the optical images really have more detail. So the radio images might have a huge diameter for their parabola, but they have such a large wavelength that the optical images and interferometers are really where we want to be, because look at that amazing detail. That is the same nebula right there. All right. When we get into interferometry, if it increases the effective diameter of the parabola, does that increase its light gathering power? Because remember, light gathering power was related to the square of the radius of the mirror. So maybe if interferometry has increased that diameter, it'll affect the light gathering power. No, it does not, because there is just so much light that has been taken in. And if you look at the light gathering power of Keck, it is actually the light gathering power of Keck 1 plus Keck 2. So 20 meters of light gathering power across those diameters. So let's think about it. Each one has a radius of 5, so there's 25 times the light gathering power, plus Keck 2 is 25 times the light gathering power, 50 times the light gathering power by using 2 different telescopes, but you don't get to use the 85 meter effective diameter that goes into the resolving power that is for the interferometer and the peaks of those light waves. That is not being gathered from the universe. It is being manufactured by software. So that is the difference. That effective diameter is used in resolving power only. See you on the other side.